Well, so today's lecture is the last in this course. I would like to mention once more that I have already sent problems for home exam to those who asked me by mail if anybody wants to, if anybody else wants to pass to solve these problems and to pass exam, then please write me to this email, and I will send you these problems too. Well, so today, the plan for today is the following. First of all, I will finish the proof of Nielsen-Baer theorem. I recall that this theorem says us that the extended mapping class group, twice extended by allowing orientation reversing homeomorphisms, is isomorphic to the outer mapping to the outer automorphism group of the fundamental group of the surface. This is for closed surface of genus at least one, and we haven't finished this proof, but we will do it rather quickly. And then I would like to discuss some ideas and sketch of the proof of the fact that the group of the group of diffeomorphisms of closed oriented surface of genus at least two is contractible. It's not the group, but it's connected component of unity. This is a result by Earl and Ilse, and it's something like 1967. And I will describe some ideas behind this, and this result sits on the theory of Teichmüller spaces from the viewpoint of complex structures on surfaces, and also we will discuss some ideas and problems which arise on this way there. Okay, so let us start with well, this is for the plan, but now let us continue and finish the proof of the Nielsen-Baer theorem. I would like to recall that last time we reduced this theorem. The only thing which we need to prove is that any homotopy equivalence of the closed surface to itself is homotopic to a diffeomorphism or to a homeomorphism. That doesn't matter. Actually, we need a homeomorphism, but we will obtain a diffeomorphism. Okay, and we proceed with this proof in the following. We proceed by the following line. First, we have chosen a Pant's decomposition of our surface, for instance, this one, but actually any of them. Then we have a homotopy equivalence of SG to SG, and by homotopy we achieve that this homotopy equivalence is smooth and is transversal to this Pant's decomposition. Then the preimage of this Pant's decomposition is a smooth submanifold in our surface. And last time we argued that for each connected component of this preimage, it is mapped by f to certain connected component of Pan's decomposition. And we can consider the degree of this mapping. So how many times this circle goes around that circle. And we discussed that there are only two possibilities. Either this is homotopy trivial, or this is homotopic, or this has degree ±1, and then it is homotopic to a diffeomorphism. No other possibilities. The degree greater than 1 is not possible. We have discussed this last time. Well, and now let us consider these two situations in more details. First of all, I claim that we can get rid of those components. So here I have this Pan's decomposition. And suppose that we have here a connected component of pre-image of this Pan's decomposition, which maps onto the corresponding onto one of these curves with degree 0. So suppose that here is degree 0. But then since we know that this f, our f, is a homotopy equivalence, this means that this f, well, there exists a homotopy inverse. And then, okay, since, look, this curve becomes homotopy trivial here, since it doesn't go around this component, it maps onto this it maps to this component with degree 0. So it becomes homotopy trivial here. Hence, it is also homotopy trivial there in the original curve. So this curve actually is homotopy trivial, which means that it bounds a disk. Among all such curves, if they exist, we can choose the innermost, and let us get rid of it. Look, consider, well, so this dashed region is homeomorphic to a disk. Let us consider a curve very close to this component. Well, let this component be beta, and we consider very close to this blue curve, which is very close, and so beta maps to this gamma, to this particular gamma, and then, okay, if beta maps to gamma, then some neighborhood of beta maps to a neighborhood of gamma. So we have here some neighborhood, which is just a cylinder, and so our neighborhood of beta is mapped to this cylinder. Gamma doesn't separate, may separate or not separate this surface, but doubtlessly it separates the cylinder. So if we restrict to the cylinder, then gamma separates it into two pieces. And of course, this because of transversality, this blue curve here and the interior of this disk lie on different sides of gamma. Their images lie on different sides of gamma. So we are in the following situation, that this blue curve is mapped, well, somewhere it is not embedded, it is mapped to one part of this cylinder, and this the interior of this disk, so this small region between is mapped somewhere in the cylinder. The interior of the disk, it may go out of this cylinder, but it is on the other part from gamma. And in this situation, actually this disk, the restriction of our F, let delta be this big disk bounded by disk bounded by blue curve. Then the restriction of F to this disk delta provides a homotopy after which we get rid of this additional component. More precisely, look, in this cylinder, the image of this blue curve is homotopically trivial, since it goes 0 times along gamma. So it actually can be contracted by a map of disk inside this half of cylinder, and this F of delta provides a homotopy between the original map and this new map. So after that, after we get rid of all such curves, the situation is as follows: that we have, look once more, we have this surfaces G, and another example of surfaces G, we have this map F. Here we have Pan's decomposition. I don't want to draw it in all details, okay. And here we have several pre-images, and for A, here we have pre-images of, pre-images of this Pan's decomposition, and we know that any of this curve beta is mapped onto one of these curves delta with degree 1 or minus 1. It depends on the orientations. We have no pre-chosen orientations, so the sign doesn't matter at the moment. Okay, but then look, any map, any degree 1 map from S1 to S1 is homotopic to a diffeomorphism. This is very obvious claim. It is not hard to see, so we can take F restrict to this curve beta, and it is homotopic to a diffeomorphism of beta onto gamma. It is not hard to see that this can be done not only for this homotopy can be extended. Actually, any homotopy from a circle can be extended to the whole surface, and moreover, it can be extended so that I don't want to prove this in details. Let us leave this as an exercise, but it is possible to extend this homotopy so that it becomes a diffeomorphism not only on beta, but on a neighborhood, a regular neighborhood of beta. So we may achieve after a homotopy, we may achieve that the mapping F is as follows. For each of the components, of the components in this preimage, it maps some regular neighborhood of this component diffeomorphically onto a regular neighborhood of one of the components gamma. So we may achieve this. Now, let us look. Is it possible that so the next question is it possible that the preimage of not of P, but of particular component of P consists of several connected components, of several, not one, more than one connected components. I would like to claim components. That I would like to say that this is impossible. Well, first of all, look once more. I would like to recall once more that we have a homotopy inverse. And well, a simple closed curve, since we have no base point, a simple closed curve, its homotopy class corresponds not to an element of the fundamental group, but to a conjugacy class of the fundamental group. And of course, a homotopy equivalence provides a one-to-one correspondence between, it provides an outer homomorphism of the fundamental group. So it provides one-to-one correspondence between conjugacy classes, conjugacy classes here of the element of fundamental group and conjugacy classes there. And first of all, we see that if there are, assume that there are two components, beta 1 and beta 2, of the preimage of the same component gamma. Then, first of all, we must say that these two curves are homotopic to each other and hence azeotopic. Indeed, both of them map to gamma with degree 1. Hence, this homotopy inverse vice versa maps the homotopy class of gamma to the homotopy class of beta 1, and on the other hand to the homotopy class of beta 2, where homotopy class is a conjugacy class in the fundamental group. So we see that they represent the same homotopy class. So if there are two or more connected components, well, then the situation is as follows, that they are isotopic to each other. So for instance, this one is beta 1 and this one is beta 2. So they together bound a cylinder, as is drawn here. Again, for beta 2, we also have a small regular neighborhood, which maps to gamma, which maps to a neighborhood of gamma diffeomorphically. But now look, when we speak about homotopy classes, we actually mean not curves, but oriented curves. So moreover, let us choose an orientation of gamma. Then we can choose the orientations of beta 1 and beta 2 so that achieve that degree is 1. And then beta 1 and beta 2 are isotopic, and isotopy respects these orientations. So the picture is like that, not like that. Oh, sorry. I would like to say that this picture is impossible. These two curves, beta 1 and beta 2, are not homotopic to each other as oriented curves. So this is not possible, since they must be homotopic to each other as oriented curves. So indeed, the picture is like that. Okay. But then look, these curves beta 1 and beta 2, their neighborhoods are mapped onto this gamma, are mapped onto the neighborhood of gamma.
Я извиняюсь, я нить немного потерял. Можно спросить?
Да-да. Я
Вот.
что-то тоже, извините, я что-то...
Почему мы считаем, что они в одну сторону должны быть направлены? Мы ведь...
Потому что они, ну, смотрите, мы их направили так, чтобы... То есть мы направили гамма, а их направили уже как получится, чтобы степень была +1. Да?
Мы именно предполагаем, что степень +1. Просто у нас... Мы пока же не отмели случай, когда есть степень 1, другой степень -1, где отмели уже.
Нет, смотрите, вообще степень 1 и степень -1 это то же самое, это зависит от выбора ориентации. Я говорю так, степень 1 превращается в степень -1 выбором ориентации. Я говорю так, давайте гамма ориентируем как попало, а бета-1 и бета-2 ориентируем так, чтобы степень была +1 у обоих изображений. Это мы всегда можем сделать. Ну, если степень -1, выберем другую ориентацию. Вопрос, почему, если мы выбрали степень не так, то картинка будет вот такая, а не наоборот, а не вот такая.
Да, тогда такой вопрос.
Да, а это вот почему. Потому что вот кривая бета-1 с одной ориентацией, кривая бета-2 с другой ориентацией не гомотопны друг к другу, как ориентированные кривые, а должны быть гомотопны. Вот это гомотопические.
Да, все понял.
Все. Okay, I was not completely correct here. I said here that this is impossible. It is not true. The true assertion is that we can get rid of this. So this is possible that, but then look, all this cylinder is mapped onto. Let us draw one of these halves by some color, yellow, yes, and then I would like to say that all these cylinder goes to yellow part or to the other part, then I draw that part by yellow. So it goes to one of these pieces of to one of these three punctured spheres, which are obtained by Pann's decomposition. And again, this cylinder F restricted to this cylinder. Let this cylinder be C. F restricted to this cylinder C again provides the required homotopy, after which we get rid of this. So the situation is as follows. that beta 1 and beta 2 are mapped to gamma, and this their neighborhoods from these sides are mapped to this side of gamma, but this cylinder is mapped to the other side of gamma, and then we can just homotop this to so we can delete remove these two pre-images beta 1 and beta 2 by applying some homotopy. Actually, it is better to look here, and it is easier to do as follows. Well, here the image of cylinder is something like that. We can homotop gamma so that it goes along these two curves, so that it avoids this image of the cylinder. But this is the same as to homotop the map in F. So in this situation, we can get rid of these two components. Okay, after...
При этом мы пользуемся тут явно тем, что мы... Тем, что уже нету этих тривиальных петель.
Да. Here we use that there are no trivial, there are no such components. Otherwise, this cylinder could go through these other components. Yes, of course. So it is important on this. So it is important that there is nothing inside this cylinder. Yes, since if there are any other components of this set inside this cylinder, then they again are homotopic both to beta 1 and to beta 2, and then indeed instead of beta 1 and beta 2 we should take two consecutive components and get rid of them. So after all of that, we see that the situation now after these homotopies, we achieve that the situation is as follows. We have here a Pans decomposition. And for each of these curves, its pre-image is a single curve here, which maps onto this gamma with degree 1. Moreover, it maps diffeomorphically, and moreover, a regular neighborhood of beta is mapped diffeomorphically onto a regular neighborhood of gamma. So after that homotopies, we achieve that the situation is like that for each component, for each gamma in our Pans decomposition. Well, to be honest, we have not proved that this component is unique. We have proved that there is at most one such component. But, well, why? So we should answer the question why the pre-image of gamma cannot be empty. Well, this cannot be true for many reasons. For instance, because a homotopy equivalence, and I recall that our F is a homotopy equivalence, should induce an isomorphism in the second homology of the surface. Isomorphism. And hence it easily follows that F is onto. indeed, if there is at least one point not in the image of F, then the fundamental class of the surface cannot be supported outside this point. It is not possible to realize the fundamental class without using a simplex which covers this point. So actually any homotopy equivalence from a surface to a surface to itself, from a surface to a surface of the same genus is surjective. So the preimage can be empty for sure. Hence, it consists of exactly one component. Well, but now this means that it follows easily that these preimages also provide Pan's decomposition here. Why? Okay, it is not so hard to characterize when three curves, three disjoint. Suppose that we have three disjoint curves. Gamma 1, gamma 2, and gamma 3 on a surface. And we are interested in whether they bound together a pair of points or not. Actually, this is just the question of their homotopy classes. Well, if they bound a pair of points, yes, then okay, we can it is better to draw this pair of points like that. Yes, this is gamma 1, this is gamma 2, and this is gamma 3. This is sphere, so there is nothing behind, and all the surface is attached from here by okay, so everything is maybe even better is well, even better is to do like that. So this is pair of points, gamma 1, gamma 2, and this is gamma 3. So this is a sphere with 3 holes, and these gamma 2 and okay. And if we choose appropriately a base point, then look, the curve going along gamma 1 and the curve going along gamma 2, and together, so if we represent them by certain homotopy classes, C1, C2, then, well, as I written, C2, C1 is the curve going once along gamma 3. So actually, what I would like to say, that if we do not think about the base point, then there is the following characterization. 3 curves, gamma 1, gamma 2, gamma 3, bound a pair of points if and only if in the conjugacy classes, sorry, it is possible to choose elements C1, C2, and C3 so that C3 equals C1, C2. Actually, I would like to write here as follows. This depends on the orientations. So if the orientations are chosen so that it is like that, then exactly C3 equals C1, C2. If with some orientations, then something like that. Okay, so this is complete characterization, if and only if. If it is so, then we easily have a pair of puns. If we have a pair of puns, then choosing appropriately a base point, we can achieve that this is true. And this characterization is preserved by homotopy equivalence. It is characterization only in terms of the fundamental group, and only in terms of its conjugacy classes. And conjugacy classes of the fundamental group is something that preserves under homotopy equivalence. Hence, okay, if here 3 curves bound a pair of puns, then here their preimages also bound a pair of puns. Moreover, the signs are the same. So in fact, if we this is true with the orientation. So if we orient curves here and we orient curves here so that the degree is always 1, then okay, each pair of puns, well, this pair of puns is adjacent to gamma 2, gamma 1, and gamma 3, and it is adjacent to gamma 2 from the left, and to gamma 1 and to gamma 3 again from the left. Then it will be also adjacent to gamma 1, gamma 2, and to beta 1, beta 2, and beta 3. But look, these signs here will be, in this situation, it will be C1, C2, C3 equals 1, or all signs will be the same. But we cannot say that it necessarily is adjacent to beta 1, beta 2, and beta 3 from the left. We can only say that it is adjacent to beta 1, beta 2, beta 3 from the same side. Fundamental group cannot distinguish between the left and the right. It can distinguish between the same side. So we have same signs here. It is better to write this not as here, but in this way, and we can distinguish between the same signs and opposite signs. So either this pair of puns goes to that pair of puns, so that either we are from the same side or we are from the other side. But okay, traveling along these paths, we may see that this okay, we have this sign that assigned to this pair of puns, we have sign plus or minus 1. So plus if it is again on the same side from beta 1, beta 2, and beta 3 as from the gamma 1, gamma 2, and gamma 3, or minus 1 if the side is opposite. But these signs for two adjacent pairs of puns should be the same. Well, the matter is that these adjacent these two pairs of puns, this one and that one, are adjacent to beta 2 from the opposite sides, and these two pairs of puns here are adjacent to gamma 2 from the opposite sides, one from the left and the other from the right. So if this one is adjacent to beta 2 from the left and this one is adjacent to gamma 2 from the left, then for these two, both will be from the right. And if these are adjacent to beta 2 and gamma 2 from opposite sides, then here also both will be from opposite sides. So up to signs here and here are the same. So we have only one sign. Either everywhere paths line from the left from the curve goes to a path line from the left of the corresponding curve, or vice versa. Always left goes to right and vice versa. This corresponds exactly to the fact that we have not only orientation preserving but also orientation reversing homeomorphism. Now, what we still need to prove? We still need to prove, look, our F is a diffeomorphism on the neighborhoods of gamma i's. Or on the neighborhood of beta i's, it is a diffeomorphism to the neighborhood of gamma i's. And it takes connected components of the complement to connected components of the complement here. But we still do not know that it is a diffeomorphism on these connected components. But now the problem reduces from an arbitrary surface just to a pair of pans. So the problem reduces to the following. We may forget about the whole surface, but now we have only sphere with 3 holes. So our surface is sphere with 3 holes. And we have here another sphere with 3 holes. And we know that this sphere with 3 holes maps onto that sphere with 3 holes, so that this F is diffeomorphism on the boundary. So F on the boundary is a diffeomorphism. It is diffeomorphism from the boundary of the first sphere with 3 holes to the second. I'm sorry for denoting them by the same letter, but it doesn't matter at all. But moreover, it is diffeomorphism on some regular neighborhoods of these boundary components. So, and we would like to, our claim is that such F is homotopic to a diffeomorphism. And this is enough. If we prove this, then our proof will be completed. We just apply this to any of the components of the complement. Well, now we need to use the same trick as before, but in its relative form. Okay, here we started from Pan's decomposition, but now I would like to choose 3 arcs here that alpha 1, alpha 2, and alpha 3 that decompose this pair of Pans into, actually alpha 3 is not needed. I'm sorry. It's better. It doesn't matter. We can take 1 or we can take 2 of them. It doesn't matter. Let us take 2 of them. Okay, 3 of them. It doesn't matter. Well, it is important that the complement of these arcs is just the union of disks. This is one disk, and this is another disk. We may delete alpha 3 and consider just one disk, but it is not important. Okay, again, let us make this F smooth and transversal to alpha 1, alpha 2, and alpha 3. Then we achieve that, okay, we have here a pre-image. But look, how here the situation is even easier. How, well, let us, these alpha i's, let us denote the union by I. And here we have the pre-image of this A. How can the pre-image of alpha 1 look like? It can be any component of the pre-image. It can be, there can be some closed components, but look, we know that on this neighborhood, this is a diffeomorphism. So there is a component of the pre-image of alpha 1 that starts like here. And also there is a component that finishes like here. And okay, it is something like that. Something embedded, sorry. And the same for alpha 2 and alpha 3. And look, for each alpha I, there is exactly one such component, lambda I. Lambda 1, lambda 2, and lambda 3. Why it is exactly one? Because we have only one pre-image of the boundary. On the boundary, it is a diffeomorphism. So this small segment has only one pre-image here. And this small segment has only one pre-image here. So we cannot have two arcs in the pre-image, two arcs for alpha 1. We can have arbitrarily many closed components, but we have only one non-closed component for alpha 1, only one non-closed component for alpha 2, and only one closed component for alpha 3. But now look, these three, lambda 1, lambda 2, and lambda 3, also decompose S30 into two disks. Okay, it's an easy assertion. Just if we have a sphere with 3 holes, and we connect first hole with the second with the third, and third with the first by any pairwise disjoint simple arcs, then of course the complement is 2 disks. Hence, all these other components, if they exist, all of them are homotopically trivial. It is impossible to have a homotopically non-trivial curve in a disk. And hence, we can get rid of them exactly as in the previous case. We can get rid from these homotopically trivial curves. And we arrive to a situation when there are no such curves. Well, but then, okay, again, we can, then this lambda 1 is mapped onto this arc alpha 1 with degree 1, and the same for lambda 3 and alpha 3, and we can again make our F diffeomorphism on these curves and on some small neighborhoods of them, regular neighborhoods of them. And again, once more the same step, we reduce our problems. First, we reduce it from arbitrary surface to a pair of pans, but now we reduce it from pair of pans to a disk. So our problem reduces to the following, that we have a mapping from disk to a disk. This mapping, F, is known to be diffeomorphism on some regular neighborhoods of the boundary. So F on the boundary is diffeom onto the boundary here, and also on regular neighborhoods. And we would like to prove that F is homotopic to a homeomorphism. Okay, and actually it is homotopic to a homeomorphism relatively to the boundary. We do not want to change F on the bound. But okay, this is completely easy assertion. There is a homeomorphism here. Homeomorphism. Which is, well, actually, first of all, any diffeomorphism on the boundary, it is better to proceed as follows. Any diffeomorphism on the boundary is homotopic to, let us regard these two pairs of D2 as the same disk. Every diffeomorphism on the boundary is homotopic to either identity diffeomorphism or just a reflection into some line. But changing orientation, we may achieve that its restriction to the boundary is homotopic just to the identity homeomorphism on the boundary. So we may achieve that F is actually we can identify this disk and that disk so that F is identity on the boundary. And now, okay, there is an identity homeomorphism, and there is this F, and they are homotopic modulo the boundary, just since we know by Alexander trick that any two homeomorphisms, any two maps that are identity on the boundaries are homotopic to each other. There are no questions of homotopy on the disk. So okay, this is homotopic to a homeomorphism or to a diffeomorphism. For disk, it is completely trivial. Okay, I'm sorry. It turns out to be. I thought that I finished in several minutes, but it turns out to be more hard to explain than I expect. Okay, by at least this finishes the proof of Dan-Nielsen-Baer theorem. Let us do as follows. The next topic is completely different. So we need to make a break at some point. Usually we make it somewhat later, maybe in 10 minutes, but I suggest that we make it a 10 minutes break now and then proceed with the different topic. Окей.
Хорошо. А можете, кстати, послать эти записки?
Ой, я все время забываю. Да, я не могу послать во время лекции, потому что мне немножко технически это сложно. Я пошлю после лекции.
Спасибо. Довольно
Ой, извините. О, здорово как. Это я только сейчас включил запись, да?